Vectors in the plane, day 4. We're going to be looking at vectors and velocity, acceleration, speed, displacement, and distance traveled. All right, let's remind ourselves what a vector is. A vector is a change in position, and in geometry we denoted it the same way here. So it tells us where to go from one place to another. So this is the initial point, this is the end. It tells us that we're going to travel x in the A in the x direction, B in the y direction, and it's just giving us a direction of motion here. The magnitude is the absolute value, so if you are to use the Pythagorean theorem and find the hypotenuse here, you would be finding the magnitude. Okay, these are the things that we're going to be working with, the calculus. Position vector. Vectors are usually written with an arrow over it if you can't write the bold part. So this is the position vector. It tells us where we're going to be on the plane at any time t. Velocity vector will tell us the rate of change at that particular point. Speed is going to be the magnitude, and it's a scalar quantity. So that's where we find the hypotenuse of the right triangle. Acceleration vector will be the derivative of the first derivative here, and direction of motion will be the velocity vector divided by the magnitude, and this is going to be a vector itself. It's going to give us an idea of what direction the vector is moving at a particular position. All right, here's a straightforward position vector right here, and we're just asked to find the velocity vector and the acceleration vector. It's just a matter of finding the derivatives. Okay, now let's study planar motion. Here is our elliptical path, and then this is supposed to be a position vector. So it's telling us at any time t, these are the positions that we're going to be in. And we want to find the velocity and acceleration vectors, which are done right here. And then it asks us right here in part B to find the velocity and acceleration at pi force. So I'm going to put pi force into both of these formulas, and let's see what this see if this makes sense to us. So this is an x direction, 2 root 2, and then a y direction half as big. So our velocity vector is going to look something like this. So this is the velocity vector for pi force. Now let's take a look at the acceleration. We're moving negative 2 root 2 and then down half as much. So our acceleration vector will look like this. That'll be the magnitude and the direction at pi force. We're also being asked to find the speed, which what we do is we take these two, we square them, and we find that the speed is root 10. The direction of motion is where we take the velocity vector at pi force divided by root 10, and here is our direction of motion. Now what is direction of motion? What will that represent? Well, it'll go over and then down half as much, and so it looks to me like the direction vector is going like this, so that is a clockwise direction eventually. Now on the next page we are going to sketch the path and show the velocity vector at 4, 0, and then discuss whether it's clockwise or counterclockwise around the origin. How does that proceed? Okay, so here is our part that we need to discuss. Here's the ellipse, and here's our position vector right here. I wrote it up here again in its vector form, and at the point 4, 0, we're looking at 4, 0 right here. We get 4 sine of t is equal to 4, so this is 4 equal to 4, so sine of t is equal to 1. And then at 0, this y value here is 0, so sine of t is equal to 0. All right, we want to find the velocity vector. Remember, we've been given the velocity vector up here. And at this point that we're looking at, 4, 0, we know that the cosine of t we have found that the cosine of t is 0. And we have found that the sine of t, when we're evaluating it for 0, is going to be 1. So our velocity vector is going to be 0, -2. Now what does that mean? It means we don't go anywhere in the x direction, but we go down. So that's going to be our velocity vector, and I want you to see that's what's being graphed here at the point 4, 0. It's a velocity vector that's going down. And we can answer the last question is, does a particle move clockwise? Because if it's moving down, then it's going like this in this direction. So this is what the curve is doing. All right, displacement and distance traveled. Suppose right here at this point, right here, this is for t equal to 8. Our position is x sub a, y sub a, evaluated a and a. And then at time equal to b, it's x sub b, y sub b. And we would like to know the displacement. Displacement is how did the x change, how did the y change. Well, you do that by integrating the velocity for the x direction, and that'll give you your change in y. Integrate the velocity for your y direction, and that'll give you your delta y. And then you're just going to start at this point, x sub a, y sub a, add your delta x to the x component, add the y to your y component, and then you'll get to your position. Now, distance travel. Distance travel is very similar to the arc length. Okay, when you use this velocity of the x direction, you're really finding dx dt. So these two are the same. This is the same as this. So when you take the velocity vector for the x position and square it, and take the velocity for the y, which represents dy dt, you're really figuring out arc length, or in the end, distance traveled. Okay, let's take a look at a particle moving with this velocity vector, and we want to find the position of the particle at t equal to 4, and what's the total distance traveled. Okay, so the solution is to find the position. You have to first figure out the displacement. How far is it going from where it was to its final position? So we're going to integrate the velocity of the x derivative of the velocity for x, and the integral for the derivative for the velocity for y. We're going to integrate that, and then we're going to get this vector. It's a displacement vector. That means to go over 8 and up 16, and this is what it's telling us to do from the initial position to the final position. And this is the initial position, 1, 5, and so we're going to add an 8 and a 16, and we'll get 9, 21 is our final position. Now the distance traveled, again using arc length, so we're going to use these velocity formulas, square them, integrate from 0 to 4. Now this is what the curve looks like, and what I'd like to do is show you how to write the position curve so you can see what it looks like. And you can see it's a really strange curve, finding the distance traveled. The calculus is helping us find this distance traveled even though there's a lot of curvy positions in it, and that it's not a function at all. Okay, so how do we find this position vector? And we do it by, one, integrating the velocity vector. So we're going to take this part right here and we're going to integrate. It's going to create a c, but we know that at x equal to 1, x is equal to 1 when t is equal to 1, so this is going to help us solve for c. We're going to do the same thing for our y, and again, y at t equal to 0, y is equal to 5. So here's our x position, our y position, and we can put it in a position vector format. And this is what we would put in the calculator too, so that we could see what this was, the path from 0 to 4. Okay, in the handout, here are some problems that typically show up on the A/B test. One, they're going to ask you for a velocity vector and an acceleration vector evaluated at a certain time. Another typical problem is finding the magnitude of a velocity vector, which you have to find the derivative of each part, square it, and what you can do is you can figure out dx dt first, dy dt, and then put them into the squaring process, evaluate at t equal to 1, and figure out our magnitude vector. And our last example is we have a position vector, and the path intersects the x-axis twice. X-axis twice means y is equal to 0. So we're going to set the y equal to 0, and we find that sine of t is equal to 1/2, and that's going to happen within from 0 to 2 pi. That's going to happen at pi 6 and 5 pi 6. So we want to figure out the distance traveled from this t to this t. What we're going to do is we're going to have to use arc length. So we're going to have to take the derivative dx dt of this and dy dt, and we're going to take those and we're going to get these values, put them in here, square them, and evaluate from pi 6 to 5 pi 6. And that will be the distance traveled. This is the end of the screencast.